reason that that's important, airflow takes a lot more power than static. So if you screw up and you overestimate the static and you don't have a variable speed drive and you don't go change your pulleys around to meet what you really need, what you end up doing is drawing more power because you're moving more air. The flip side of that is, let's say you underestimated. Let's say that you said 3.5, but there was really 4.5 inches. You're going to take less power. You don't have to worry about overloading the motor because you're going to be operating back up here, and now you won't move enough air. And the airflow is like 2 to 3 times more in terms of the power usage as opposed to overcoming the static. And pumps work pretty much the same way. So there's wisdom in trying to get the static right. Or if it's a pump, the head right. If you grossly overestimate and you're not on a variable speed drive, you're going to have some massive pulley changes to do at startup to get the thing to work correctly. Okay, so that was just a quick review while everybody is mentally. Any questions? You can raise your hand or not, or if you need.
Yeah. Explain a very, very quick layman's terms definition of the difference between a variable speed drive and a variable frequency drive.
Same thing. So a variable speed drive, what it changes is the hertz. So you guys all know that we, in our country, in North America, we use 60 hertz power. Almost any place that was part of the modern British Empire uses 50 hertz power. And then other places, depends on who conquered them. Like the Philippines uses 60 hertz. But the hertz is, on that little waveform, relates to the period. Yeah. And what a variable speed drive does is it cuts it down. So if we're standard, full speed, normal speed, we're at 60 hertz, a variable speed drive would slow that down to 55 and 50 and 45 and so on in order to get the thing to spin slower, right? And that's how it does it is a much bigger discussion, but the result is it lowers the hertz value. And if you're going to overspeed the motor, the hertz go up. We have equipment today that's designed to work 60 hertz as a normal thing, but like compressors and VRF systems, when they're in heating mode, can go up to double speed. And then they'd be running, instead of 60, they'd be running like 110 hertz. Now, they have to be built specially to do that, but can they do that? Yeah, they can do that. You can alter the hertz and change the motor speed. Okay, so, and again, any other questions, let me know. So the next thing that where we left off was curbs, roof curbs. Let's talk a little about roof curbs. Excuse me. The typical cheapy rooftop unit, 5-ton, 10-ton, whatever, is usually called a downshot. Why do you suppose it's called a downshot?
Because
the air is going down and the return air is coming up, right? That's as opposed to a side shot, where the air is doing that. Okay, downshots are on curbs. Let's go get food. I'll go first so I can talk while you're eating. Well, Rich went first because he's swift. On top of
I'd like to consider myself an inspiration.
well, you were giving it thought. Do we have napkins over there?
We have some napkins over here. We'll grab some more.
Nobody can eat these without it.
Somebody can. Someone dropped a crouton. Got a crouton down.
So Caleb, we had this conversation before, but you are permitted to eat.
Oh, boy.
How you doing, Mr. Hardy? Excellent. Learning anything at all?
Yeah, learning about sizing a new supply fan. There's this fan we're replacing at Fox in the penthouse of building 103 with Chad.
The fan wall project you're
Yes.
talking about.
And we know the design conditions, we know that it needs to be a 4.5 inches of water column.
Now
Well,
your
private inches of static.
And it's at 100,000 CFM for the supply fan, so we're replacing it with a fan wall.
Yes, sir. Thank you. As soon as I finish eating, I will be back up with the board. Fair enough. Right. So, it has been reported to me that everybody's watching me eat on the live stream.
Yeah.
Thanks, Jim.
Oh.
So, what was the CFM again?
100,000 CFM. It's really neat though, because like the whole building is like an air handler. That was the coolest part. So now we're putting in those fan walls.
How are you going to control that? Well, let me back up. How many fans are in the fan wall?
There's maybe like 14. I have to check
I get
the.
a couple of days.
You know.
Or no, I think.
We need to talk about fan walls too. For some reason, I looked it out. That's their side.
That's all bad all week, right?
I'm just gonna edit this out in post.
But not in the context of like.
It can be controlled with like an analog signal or a digital signal. I was reading the IOM, like an analog signal that goes from 0 to 10 volts or something.
Analog.
And it said something about Modbus or BACnet IP.
Now those are Jeremy.
And each plug fan had 3 connections, one for pressure, one for power, and one for control signal. And it all went into this control box.
I'm just gonna take the whole set.
But that's kind of beyond what I have to know for what I'm doing.
You're a rabbit
Well-
in the feet.
But you always want to understand it all, right?
Yeah. So they're all ECM motors.
Although this would be good.
Boy, that's a good point. Yeah.
Just
I
not.
know, we have a number of proposed people here, but going the difference between analog and
I'm not
digital.
shaving you. I mean, it's your choice to be. So you're not shaving.
How are the beats coming along? Are the insects eating the beats?
Last 2 weeks they've gone nuts. I want to get your side about that.
You don't reroute me, say, hey, you know,
That's exciting.
it's like 5 minutes.
I see your.
I like watching things grow.
Yeah.
Okay. So while you guys are eating, I will get started. So the gentleman in the front row here have pointed out some other fan-related things. And so rather than going straight to what I was going to talk about, I'm going to detour to these fan-related things that other people just pointed out. We have a big project right now at Fox where we're replacing a big centrifugal fan with a fan wall. How many people have a clue what a fan wall is? Oh, I'm seeing some hands. I'm feeling better. How many fans are in that fan wall? 14?
Or no, I'd have to look at this.
That'd be a hell of a lot of fans in a fan wall. Could be.
Maybe, I'd have to look.
So we'll make up a number. We'll say there's 8. Okay? So you got a honking fan doing 100,000 CFM. And remember, we talked about trying to get, a long discharge, trying to, avoid having any big change on the discharge of the fan. We had this conversation, right? A fan wall is a case where, there it is, where you don't have to really mess with that too severely. I mean, you don't want to put it right on the discharge, but what a fan wall does is you've got a whole bunch of individual fans mounted crossways. So they're single inlet, and they blow out into this plenum. And then off of the plenum, you run your duct wherever you're going to run it, whatever you got to do. And so if there were 8 of these, and it's 100,000 CFM, then they're each 12,500, right? Just 100,000 divided by 8. The issue of an analog or a digital signal came up. We live in an analog world. Everything in our world operates in an analog manner. Everything. But most of our communication is digital. So in the controls world, we try to figure out, does it make sense to try to use digital to simulate analog, or do we just create an analog signal? A 4 to 20 milliamp signal or a 2 to 10 volt DC signal is an analog signal. But the wires aren't transmitting analog. The old gauges that we used to use, pressure gauge or an amp meter or something like that, those are all analog. The cell phones that we had up until 1991 or 2 were analog. And their signal was not as good because a digital signal is a more robust thing. It can overcome a lot of things that an analog signal has more difficulty doing, and digital is less expensive. So we went to digital signals. But ultimately we're producing, if you're going to watch a video or you're going to talk to somebody, your world is analog, right? So the question was, are we taking an analog or a digital signal into these ECM motors? So part of that is understanding what's an ECM motor. ECM motors, the easiest way to think of an ECM motor is that it's a multiple speed motor, not a variable speed motor. When you take a standard motor and you put a variable speed drive, it changes the hertz like we were talking about, and in a analog manner, this digital device, the variable speed drive, changes the hertz and therefore changes the motor speed. ECM motors don't work that way. They have, the easiest way to think of them is they have a whole bunch of speeds. So let's just, do you happen to remember off the top of your head how many speeds this thing had? Speed inputs it would take? I mean, maybe it's 6, or maybe it's 8, or maybe it's 10. And you give it a different digital signal, and boom, you've got a different speed. Now you can have an interface that would accept an analog signal and move it to the closest fixed speed, and that works fine. The one thing I want to caution you about, and we learned this the hard way because we put something in that didn't work. Nobody told us when ECM motors became really common here 3 or 4 years ago, 5 years ago, whenever it was, I lose track of time. A standard three-phase motor has a boatload of starting torque. It's why your hybrid car or your plug-in electric car has so much torque from a dead stop. You tromp on that thing, you could almost do a standing broad jump with your car, right? Because it's got electric motors. You're used to having tons and tons of torque at low load. ECM motors don't. They are weak sisters. They do not have the starting torque at startup that a conventional three-phase motor has. So here's a project that we did that will remain nameless. We had a air handling unit serving a surgery center. And this air handling unit had a real big beefy fan in it because it not only had pre-filters, but then it was blow through. There's a cooling coil, there's a hot coil. We had a hot deck, we had a cold deck. We had super duper secondary filters built in. I mean, this was big motor, big air handler. But up on the roof, originally, there had just been an outside air shaft that came in with dampers to regulate outside air. And we weren't able to assure the proper amount of outside air. So, well, that's not true. We were able to assure it, but we couldn't condition it. Our climate has changed a good deal. When I started at Western Allied in '94, there was no such thing as humidity in July. You might have a day or two where you hit maybe 76 wet bulb. Last summer we didn't have much either, but that was the exception because for the previous 10 years, early July was miserable. And in fact, 2 years ago was the worst I've run into. We went 3 solid weeks in early July, or very last day of June into July, where it was between 76 and 78 wet bulb peak every day. I mean, this is like Midwest humidity. It was bizarre. Okay? But when you've got to control humidity level in a surgery suite, and you've got a fair amount of outside air, because there's requirements for that in a surgery suite, medical requirements, we ended up wanting to put in a cooling coil and a filter, 100% outside air, and bring that down, and pre-cool, basically knock some of the moisture. And we'll talk about coils and doing that here a little bit later today. But we wanted to pre-cool. Well, so this is a ECM motor. If this fan is shut off for any reason while this one is still running, if you've got a live fan in the duct system and you turn off the motor, but it's hooked to some other system with another fan that's active, you're going to still have some air going through it. What happens to the fan wheel? It starts to spin. And often, depending on what's going on, it might be spinning backwards. That's really common. So in this case, let's say somebody shuts this off to change the air filters. Or let's say there's something in the control sequence that causes this to shut off at some point. But this one is not off. And this starts spinning backwards. In the old days, with a three-phase motor, this could be spinning backwards. We turn it on, and unless that fan wheel was just massive with lots of mass, the three-phase motor would be able to stop it and then start it turning the right direction. It had that kind of starting torque. ECM motors don't. As a result, if this gets shut off and then it's turned back on, it will continue to spin backwards, because that's what motors do if they can't overcome. Single-phase motors are famous for this. If you can't overcome the inertia, thank you, then you speed on up and you're running backwards. So if you take a forward curve fan and you spin it backwards, either because somebody messed up on the motor connections, because three-phase power, if you flop any two, you'll just reverse the rotation. Okay? forward curve fan, rough order of magnitude. If it's spinning backwards, what percentage of the airflow is it going to move? It's going to move air, but not as much as it would if it was spinning the right direction. Anybody have a guess?
A third?
Better than that. It's more like 2/3. You're going to be 65 or 70% in that ballpark. So if you're trying to get so much outside air to meet some medical surgery standard or for a clean room, because they often have separate fans, or some application where you actually care about the amount of outside air you get, and you're using an ECM motor in the little guy, the chances of it being able to go off and on without coordinating with this going off and on are about 0. Okay? Because they are so weak, and we didn't know that. So then the question is, what do you do about that? Well, what you do about it is somewhere in that duct, where it was convenient, you put a damper that's motorized. And if this is going to go off, that damper goes shut. And then, when you tell this thing to come on again, the damper stays shut, it gets up and it gets moving, and then the damper opens. Because if that damper is shut, now it won't be spinning backwards. And it will actually come up and start and run. Okay? Whenever I hear ECM motors, this bad experience, we had to go in, retrofit the damper, change the controls, do all kinds of stuff, and even then it wasn't 100% reliable because there was leakage through the damper, and it would start to, and even a little bit of spinning you would get through the damper leakage, this weak little ECM motor could not overcome. So be aware that when you're using ECM motors, if it's just a freestand, it's just a batch of ECM motors, you're fine. But if they're being pushed and they're going to be spinning because of some other fan operating in their system, you really need to evaluate that one. Okay, so the fan wall is just a wall of fans. And they are single inlet, they're pressurizing the plenum, and the duct goes away. They are less efficient. They can be pretty good to control. But remember, we were talking about they will spin backwards. And so if you've got a fan wall with a bunch of fans, on the discharge side, if we looked at that on the end, here's our fan sitting here, right? The motor and a fan wheel. We have to put a motorized damper on the discharge of every one of those. Because when you take them offline, you have to close the damper. Now, you can drop the speed way down, and you may prefer in your control sequence to keep them all active and just keep lowering their speed, but eventually you'll get down to whatever the minimum speed is. And the minimum speed may not be enough to overcome the external static pressure. Because remember, if this is a VAV system, you're pressurizing the plenum, the duct's going down into the building, 2/3 or so of the way down here, you've got a pressure transducer, and that's what you're using to control your fan speed, right? You're maintaining duct pressure so all your VAV boxes have air. Well, when you keep dropping the speed of these things all down, you got all of, if you had 8 fans, you got 8 of them, you keep dropping the speed down, you can control to get enough air that way. But at the bottom speed, will you be able to generate enough static to maintain your static pressure down here in the building? Good chance you won't. And so part of your control logic is going to be, okay, if I want to maintain some number, whatever it is, adjustable, right? But if I want to maintain some number down there in the duct, first thing I do is I go from, if it was at full speed, because it's morning cool down, it's Monday morning after the 4th of July, or Tuesday morning, whatever day people go back to work, after a 3-day holiday in the summer, that building's going to be hot. And so, well, I say it's going to be hot. As Mr. Sanderson pointed out previously, Title 24 says you get up to some temperature and you start pre-cooling, but people often disconnect that because, hey, that's money I have to spend. Nonetheless, you come in some Monday morning and it's hot, And so all your fans are going to be going full tilt boogie, cooling off the building until the building gets down to reasonable temperature. And then they'll start to back off. Okay. So you're going full tilt boogie, and then you slow down 90%, and then 80%, and then 70%. At some point, you're not making static anymore. And then what happens if the demand keeps going down? At some point, you're going to decide to take some of these fans offline. And maybe by experience, one of the brilliant minds in the controls department, you know, Mr. Slobodkin or Mr. Arvid or Mr. Mentalva will tell you, no, what we typically decide to do is we'll get down, and when we're below half or we're below a third, we'll then just start taking whole fans offline, which means closing the damper and then shutting off the motor, okay? Because you've shut the damper, you're not, remember we got a whole bunch of these in a row, right? And so here, this one's open and this fan's running and we're pressurizing this plenum. It'll inevitably start going back through here and spinning the fan backwards if we haven't shut it off. And that's got to have a decent seal, because if there's any leakage at all, it will start the fan spinning backwards. And if it starts the fan spinning backwards and it's an ECM motor, it can't stop and go back the other direction. So you have to have some pretty darn good low leakage dampers there, motorized and controlled in a sequence that when you take them offline, first you shut it, then you turn off the motor, and then you sit there until at some point later you need that fan to run. You start the fan, you get it up and going the correct direction, and then you open the fan, open the damper. Okay? This was a hard-learned lesson. There are other ways to do that. I have wondered when the manufacturers would make widely available some kind of a mechanical clamp that would stop the fan shaft from spinning. I have read about those, but I have yet to ever see us use one. Now maybe we've used one and I didn't see it. That's possible. Okay, now we're back to rooftop units. So I want to talk about roof curbs, and this seems like a really simple thing, right? But I want you to avoid making a mistake. Here's the rooftop unit, and it's sitting up there on the roof, and we got a roof. If it's downshot, we almost always have this unit sitting on a curb. The exception would be if we had some kind of expanded metal steel frame and are up there and we duck down from there and then penetrate the roof. Once in a while you'll see that, usually with really big honking rooftop units. But for little guys like, you know, the 5, 10, 20-ton stuff that we see all the time, that's usually going to be a downshot and it's going to be on a curb. Now, when I was a carrier guy 35 years ago, and you opened up the catalog, or you opened up your price pages, and somebody ordered this 7.5-ton rooftop unit from you and wanted a curb because it's a downshot, you would have a choice between an 8-inch, an 11-inch, and a 14-inch curb. And obviously the cheapest one was the 8-inch, and then the 11, and then the 14. And the dumb carrier salesman who had just started and just didn't know any better would always use the 8-inch curb. And sometimes that worked, especially for new construction. See, here's your roof surface, and what you do is before you put the final roofing on, this is just the structural roof. You'd have the hole that the return and supply duct were coming through, and you'd have this curb that did this. And if it was an 8-inch curb, that'd be 8 inches high. And then it would go across, the rooftop unit would go across, and you'd have a curb went all the way around the perimeter. That's pretty simple. So what goes on top of the structure?
Insulation.
Insulation. And then some kind of a membrane that isn't going to leak water. And you attach this curb however you're going to attach it to the structure, and then the layer of insulation comes in, and then your waterproofing layer comes in. So 35 years ago when I was the carrier salesman, the energy code requirement for this insulation was not much. In fact, if it wasn't conditioned space, there was virtually no insulation requirement. If it's conditioned space, then there was some requirement. Well, that's changed over 35 years. And so where this might have been, I'm going to say maybe 2 inches of insulation, and then whatever you allow for an uneven application of the waterproofing membrane, ½ inch, whatever, probably less than an inch. So maybe it's 3 inches tall. That was then. It's not at all unusual to see, depending upon what they're using for insulation, a lot higher thing. And that's if it's new construction. There's a lot of ways to re-roof a building. And sometimes you'll see people not strip all the old stuff off, they'll just put another layer of insulation over. Short answer is, I would never use today an 8-inch curb for anything, because you've got all of this. Now, do engineers ever specify a curb height? Do we ever specify a curb height? Yes! I saw a yes, I saw a nod. That just makes me feel good. You will frequently find that they don't. If they didn't, how do you decide what curb height you want? Does anybody ever look at architectural plans on it? That should tell you something about the roof. Will it? Well, probably not, because architects as a whole aren't as thorough as they used to be either. But I don't like 8-inch roof curbs. I don't know how any of my partners feel about this because we haven't had that conversation. But for me, if the choices are 8 or 11 or 14, I'm probably going with an 11 unless I have some other knowledge. Why is that important? Because your submittal that you get from the vendor that you're buying this stuff from should indicate which curb they're providing. You always want to check that. And if you find that it's down here, hell, we even had, for a while we were offering a 6-inch curb. I don't think they do that anymore. But if you're down under, in that range, you need to, at the very least, you need to raise your hand, question it, and find out whether that will put you in trouble or not. On a brand new thing, you probably would get away with it. Now, what if it's a sloping roof? You can buy sloped curbs that are like this on one end and like that on the other end. But in order to do that, you have to tell them the slope of the roof. In the real world, what ends up happening is usually they will be using wood to do some level of building up.
There's also adjustable ones.
And there are adjustable ones as well. If you've got a sloped roof and a downshot rooftop unit, in your submittal review process, you need to know what it is that the guy thinks he's giving you, and you need to go to whoever's in charge of that project, and you need to say, this is one thing I would always go to whoever the senior PM is on this job. Say, look, this is the roof curb they're giving me. Anytime it's a sloped roof. Flat roofs are really pretty easy. But a sloped roof is not. Okay? And we have some, out there in Los Angeles, California, we have some pretty substantial ones. Now the bow truss roofs, does everybody know what I mean when I say bow truss? So you know the shape of a bow, right? When you're firing an arrow, you know how it's shaped like that. Well, you turn that over and a bow truss roof is shaped like that, and the truss that is holding it in place is, built typically out of wood, because these are all from the 40s and early 50s. Hollywood is full of these. So you've got some kind of a bow truss. But here, if you're going to do downshot, and that's not unusual, usually the roofer will actually build a wood frame specific to that so that you are mounting on a flat surface. That's a good answer. Okay? You don't want to try to deal with a sloped curve on something as steep as a bow truss. I mean, a bow truss you literally can't stand on if it's slick. You can't even stand because I mean, it's like this. So, roof curves. Now, I left out something in this height issue. What kind of a P-trap am I going to need, and how much distance do I need for my P-trap to be able to drop? If it's a little 5-ton rooftop unit, there's probably not enough static involved. You guys kind of remember from our previous conversation how deep the trap needs to be, and it's based primarily on how many inches of static we're going to do. Well, for a little bitty package unit, that's probably almost not a consideration. But as you get bigger, and we'll do 120-ton rooftop units. Pretty soon you're talking about a real fan pushing a real duct system. You're talking about a fan that's doing 3.5 or 4 or 4.5 inches total static, and then depending upon, it's usually a draw through. But when you look at all that and you figure out how deep the trap's going to be, that's another thing that does figure into what your required curb height's going to be. Let me tell you about another error that occurred on one of our projects. I'm not going to say it was our error, but I will tell you we never thought about it and we never asked anybody else about it. There's a very famous building that we have serviced since we converted it. It was originally a Fedco store. And this building that was originally a Fedco store had 6 40-ton rooftop units on it. And of course they had condensate drains and a whole bit, downshots. Well, when the new owner bought this Fedco store, they decided they were going to convert it to a police department. New loads were run. And this was an old, the dime is starting to drop for a few people on where this is. The old units were, God, we did this conversion in like, I don't know, 02, 01, something like that. So these units were probably 25 years old then. So these were from like late 70s units. And so their efficiency sucked, right? It was just terrible. But because of that, there was enough electrical service to put a 50-ton in place, and the existing electrical service would handle that. So why wouldn't you want more tonnage? And there were actually, when you did the load estimate, there were portions in this police department that needed more cooling than what the old Fedco store had needed. So it all made sense, and so what ended up there were 6 50-ton units. But nobody thought about the condensate drain. That's plumbing. Well, we wouldn't do it. Well, when you look at condensate draining sizes, if you're up to 20 tons, you're supposed to have a 3/4 inch condensate drain line. If you are greater than 20 tons, up to 40 tons, it's 1 inch. If you're greater than 40 tons, up to 90 tons, it's 1.25 inches. And if you're greater than 90, up to 125, it's 1.5 inches. You're not likely to see much bigger than that, so I'll leave it there. Well, we went from 40-ton to 50-ton units, didn't we? What happens to the code condensate drain size between 40 and 50 tons? It goes from 1 inch to 1.25 inches. We had no problems for years. I told you we did this in like 01 or 02, whenever we did that. But a dozen years ago, it started getting humid in early July. And there was more humidity in the outside air being brought in, and so there was more condensation. And pretty soon, we're overflowing a couple of these lines because the drain line size is not enough. Now, Code is not brilliant. Code tends to err on the side of being conservative and being safe, right? So do you always need exactly that to make it work? Well, hell, if you're in Death Valley, you'd never have any condensation at all, right? So it would be irrelevant. Code is built around what is a likely worst case humidity scenario, which Southern California never had before. This is Universal Plumbing Code, which is UMC, UPC. So it wasn't a problem. But another statement about how climate has changed is that we started overflowing these lines. We're not cheap guys to rework. And think about how high a Fedco store is, right? So that's how tall the roof is. That's where the, think about how many feet of condensate drain you've got to get over to wherever you're dropping down and then where you're going below. We did one of those and it solved the problem. But by the time we'd done that, and everybody nodded and everybody said, yeah, that's good, we solved that problem. By the time we were done, we were through the end of July, we were into August, it wasn't as humid, and the problem went away. Okay, fine. Next year, the one we did still worked, but the other two units were overflowing. Only reason I bring that up is that when you do a retrofit, if you're going to change equipment size, remember to check the condensate drain line, especially if you're breaking sizes. You're going from a 20 to a 25, or you're going from a 40 to a 50, or you're, okay? It's one more thing you got to check.
And the ductwork.
Pardon?
And the ductwork.
Yes, we put in all new ductwork.
Oh, okay.
We did, but we didn't touch the plumbing. And would it have been in our contract to do that? Well, we could have done it. You know, we could have done it. Nobody thought about it. That's really what happened, being honest. Okay, one more plumbing code thing. If you're going to put a fan coil unit above a ceiling, you got a cooling coil, you got a filter, you got a condensate drain, right? If you're going to put that above a ceiling, there's 3 ways to meet the drain requirement to avoid an overflow into the space. One thing you can do is put an auxiliary drain pan under it. That's legit. Almost all of these are also going to have, if I blow it up, this little opening is usually 2 heights. There's usually 2 connections. One's higher than the other. Usually by about the diameter of this bottom one and then the next one. So this one goes to your P-trap and out. This one you pipe someplace visible. Out into a hallway is a great place to put it. You turn it down, you poke it through the ceiling tile, probably have somebody put one of those nice shiny chrome round things around it to make it look pretty. So what happens if this drain line plugs?
Secondary.
The secondary, now the water level rises in the pan, right? And eventually it will come out of this one, and now it'll be dripping out in the hallway. And somebody says, oh, we have a problem, and somebody goes and looks and figures out that you've got a plugged drain line. Drain lines will plug. It's going to happen. So that's a legitimate way to handle it. The pan is a legitimate way. And the other way is, and by the way, you could pipe this pan out to a visible location, but my memory is, and I have already told you, I am not the code maven, but my memory is it's not required. If you just got a pan, you're legit. But let's say you got a pan and then you put moisture detection in there. And we talked, I think, before about using the button versus using the cable. Did we have that conversation, or am I making it up in my brain? I'm seeing blank looks, so I'm making it up in my brain. Okay. That button, the way it works, if it comes in contact with water, it closes a circuit. Or
Opens the circuit.
opens a circuit. And there will be, on the little control board for this little thing, terminals to hook it to, that when it gets moisture, it cuts off the unit. And that's totally legit. It doesn't need to drip somewhere because people will start to bitch and complain because the unit is no longer cooling, right? Then you'll get a complaint, and then somebody will go investigate. The cable is just like the button, except it's got a jillion little buttons within the cable. And it lets you cover a much broader area. Costs a lot more than the button. But for example, if you've got a crack unit, computer room air conditioner, crack. If you've got a crack unit on a raised floor system, there will be a cable under that thing because you don't want the water getting down into your cabling. Okay. So there's three ways, right? We can put a pan under it, auxiliary pan, do that a lot. We can pipe a secondary drain, do that a lot. We can use moisture detection. Don't do that quite as much because it's just a little more involved and usually costs a little bit more, but it's just as legit. Any of those three ways will meet code. So we did another building for a general contractor. The GC actually owns this building. It's the gentleman's who founded the company or who actually made it successful. It's his building. He rents it to this company. What's the standard ceiling height in general?
9 feet. 8 feet.
8 feet. The standard ceiling is usually 8 feet. Now, you'll often find where the architect wants it higher, or you're in a big barn-like room and they want it higher to give more space. But 8 is typical. So as a result, back in the day, when I was young, the typical floor-to-floor height in a building was 12 feet. That let you have, 6 or however many inches for the floor, so that gave you like 11.5 from floor to the bottom of the structure. And if you had an 8-foot ceiling, that meant you had 3.5 feet to work with. Well, as people started building buildings cheaper and cheaper and cheaper, one of the things that they realized is, well, if I shrink that down, the building's not as tall. There's also a lot of code differences that occur at 75 feet of height without going into a whole lot of detail. There's a lot of them. So if you shrink it down, if I take 75 feet, and let's say that in the lobby I want to have 12 feet. That's pretty typical, right? I want to have more height in that lobby area. So if I take 12 feet off of that, that leaves me with 63. Whether I get 5 floors or 6 floors out of that building relates directly to how much ceiling space I'm going to leave myself. And how much more leasable space do I get if I have one more floor, right? So you end up a lot of times today with a fairly cramped ceiling. So let's say that I'm doing this building for this general contractor and I got water source heat pumps. That's a cheap, reasonably efficient way to do things. It has other drawbacks, but it's not bad. Okay. And I got an auxiliary drain pan underneath. And I've only got a little over 2 feet. I don't know, maybe I got 2.5. So your condensate drain, how much height do you think you need for the condensate to flow? I don't remember the plumbing thing. It's specified in the code. You've got to have a, so many inches in so many inches fall to meet code. And if you scrape it down at the very minimum like that, if the guy doesn't do a perfect job of putting the line in, it's going to have some dips and it won't work right. So you want to actually do a little bit better probably even than the code says for condensate drain. And if you've only got this much space and the unit itself is 22 inches tall, how are you going to get the condensate to drain? I heard you say it.
Condensate pump?
A condensate pump. So condensate pumps are these little devices which I'll greatly oversimplify. They've got a little silo. They've got like a ping pong ball. The water comes into the basin that's got the ping pong ball. When the basin fills up high enough and the ping pong ball goes up high enough, it makes a circuit and the little pump motor pumps out the water. And typically what you'll do is you'll be running a condensate line almost, I mean, you'll be hanging it just maybe this high off the ceiling with a little spout that goes up. And you'll take this and you'll run maybe some 3/8 soft copper around into the top of the condensate line that's running high. And that gives it the fall. That's usually what you do. Now, when you're buying a condensate pump, I wouldn't normally, unless it was a really big unit, I wouldn't worry about how many GPM it'll pump. But the relevant thing is, how much head will it overcome? In this application, you're only bumping it up a couple of feet. It's not a big deal. But what if you're on the second floor and you're trying to get it up through the third floor and out into drains on the roof? Well, now you need more feet of head, right? So anytime you buy a condensate pump, there's two things you got to know. The first is how many feet ahead, and will that work for whatever I'm doing, wherever I'm taking the water. But the second thing you need to know is the voltage. If this is a 460 volt water source heat pump, there will be a controlled power transformer in there, but it's a very good chance it goes from 460 to 24 volts because that's what your controls are using. Will there be enough extra VA, volt amps, that's how they rate these, right? Will there be enough extra VA to power the condensate pump? Well, there should be, but manufacturers, like everybody else, they're skipping stuff down to the bare minimum they need to get by. And what you don't want is you don't want every time the condensate pump turns on, your voltage drops from 24 volts down to about 17. That's not good for, for the circuit board and how it operates and what it does. Okay? So you might have to run a separate electrical service. And you certainly will if you wanted, for whatever reason, let's say use a 115 volt condensate pump. As you might expect, the higher the voltage of the condensate pump, the more head it'll push. If you've got to push a bunch of head, you probably aren't going to make it with a 24 volt condensate pump. You're probably looking at using 115. If this is 230 single phase, you might simply go with a 230 volt condensate pump and power it right off the unit power. But then, and again, you don't have to put any controls in for it. It's just going by the ping pong ball float. It's not really a ping pong ball, obviously. Yeah. Okay. So condensate pumps, head and voltage. And the voltage question comes back to, well, how am I going to power this thing? And how much power does it take? And do I think I've got enough left in the control power transformer? For 2 feet, a 24 volt condensate pump will work just fine. Do I have the VA to drive it? I would hope so, but do I? That's another area where you don't want to put in 40 of those and then suddenly find out it won't work. Okay. Very good. We got just enough time now to talk about heat exchangers. And this is how you pipe a cooling coil. And we're going to talk about cooling coils, but then we'll apply it to every other heat exchanger on the face of the earth, because they're all the same. So here's my cooling coil. And let's say it's a 6-row. One, two, three, four, five, six. And then it just keeps on going, right? There's a bunch of different circuitings. Typically, you expect that your equipment vendor will pick this for you. What you typically tell the vendor is, okay, this is a size 21 air handling unit, and I'm going to move 11,000 CFM, and the outside air, let's talk about that. So let's say we were bringing in 15% outside air. And the return air from the building, if it's 72 on the wall, what's the temperature up in the return air plenum of the ceiling? Más o menos. Well, first of all, is the temperature just right below the ceiling going to be the same as it is here on the wall? Heat rises, doesn't it? So if it's 72 here, it's probably, I don't know, 74 up there at ceiling level. And then we'll get some return air, egg crate grill, whatever, and we're pulling air out of the room through the ceiling plenum. And that's going to include the heat from the lights. Now, although these are putting all the heat into the space. See how the bulb is here? That's a lot more common with LED now that we've got LED. Used to be, they would, if it was any kind of fluorescent, you'd have and you still see a lot of fluorescent lights out there. It would be a housing with holes in the top so that the heat could rise from the bulbs up into the ceiling plenum. That was the typical, okay? Like I say, now that we're using LEDs, they put off very little heat. I won't say no heat, they put off some heat, but a lot less than fluorescent bulbs would have. And when I was in my 20s, we weren't using a magnetic ballast, we were using or did I get that right? The old style ballast, now I don't even remember what they were called. But the old style ballasts, they put off a shitload of heat. In fact, you would bump whatever the wattage of the lights were by 25% just to cover the ballast. Long story short, today, if it's 72 in the stat on the wall, it's probably 74 at the ceiling, it's probably 75 in the room. So we got 75-degree return air up in the plenum. We're putting in air at 95, let's say, because it's hot outside. That's a 20-degree difference. And if it's 15% outside air, that means it's going to be 78-degree mixed air. So here we got 78-degree mixed air coming in, and what temperature do we want to make in a VAV system as a default number? Somebody please say 55.
55.
Thank you. Okay. Now, let's say that I'm actually designing this thing as though energy counted, and that value is important to me. And let's say I was putting 42-degree water in, and I'm taking a 16-degree rise, so I've got 58-degree air or water coming out. What's it called when the thing you're heating is going this way and the force you're using to cool it is going the opposite direction?
Heat exchanger.
Yeah, it's a heat exchanger. It's counterflow, right? Because you've got what you're cooling going this way, and what you're using to cool it with is going back opposite direction. So the 42-degree water is on the leaving end. I drew this piping it in the bottom, but there's no magic of piping it in the bottom. The manufacturers use the same coil for a left-hand air handler as they do for a right-hand air handler. They just flip the coil over. So if it's piped from the bottom as a right hand, it's probably piped from the top as a left hand, right? So you've always got to pipe it counterflow. This would be a 6-row coil. Now we've got a header here, and the water's going in the header. If you're feeding every coil in the front row with water, or every tube in the front row with water, and then on the back side, there's a U that does that and flips it around to the next row, and then on this side there's a U that does that, and on the back side it does that, so that we go through. Okay, that's a full circuit because we're doing the whole full face of the coil is getting water. If we really got to make this water, this air cold, we might have to go to a double circuit. And then we're feeding the front 2 rows. And so this one goes then to here. And this one goes to here. And the same thing below it. the penalty you get for that, because now we're putting 42-degree water in the last third of the coil if it's 6 rows, right? The penalty for that is you can't get the high rise on the water temperature. You just can't, because it's not exposed to the air as much. It's only making 3 passes to get through a 6-row coil. On the other hand, let's say your priority was that you wanted a high rise. Why would you want a really high rise? So, the formula, BTUs equals 500 times delta T times GPM. If you want to take a really high rise, make this number big, that means you're making that number smaller, right? They're directly proportional. If you took a 10-degree rise versus a 20, at a 10-degree rise, you'd need twice as much water flow. At a 20-degree rise, you'd need half as much water flow. Think about what that does to your pipe size, your pump size, the amount of insulation you got to put on the pipes, the weight of the stuff, the labor. The higher the rise you use, the less expensive it is. Your limitation is probably how big of a coil do you put in, because the higher the rise, usually the more coil you need. That's the trade-off. And can my chiller do that? You know, you'll get to a rise that's so high the chiller can't do it anymore. But this is counterflow. And everybody now knows that it's not automatic that you pipe a coil from the bottom, right? You pipe a coil counterflow. Every pipe fitter should know to pipe it counterflow. I will say that it would be really unusual for one of our pipe fitters to make that mistake. But the non-union guys are usually using plumbers to pipe. And plumbers don't know about counterflow. There are a lot of plumber jokes out there. I won't bore you with any of them. But nobody teaches counterflow in the plumbing training center. That's not part of their curricula. Okay. Last point I was going to make is that counterflow is not limited to a coil. It's always counterflow with any heat exchanger, and let's take a cooling tower. If I've got a cooling tower with a propeller on the top, it's pulling air out of the, actually low, typically it's pulling it from way down here. So forget that. Got some louvers here. How's the water being introduced? Somebody say from the top.
From the top.
Thank you. You guys are great. So the return waters come to the cooling tower. You've got some kind of a spray tree or tray or something that's dripping it down. It goes through the fill, which is like honeycomb, right? Or maybe it's like a whole bunch of vertical plates together. The air is counterflow. It's coming down here to the sump. It's trickling down. And the goal is to get this water down to a temperature that we can send back to the chiller. On a design day, it might be coming back at 95 and you might be cooling it to 85. Common numbers, okay? So, counterflow. I was looking through material to try to use for this class, and I pulled out some of my old Carrier stuff from the late 70s and early 80s. And I found a memo from 1979 where the air handler group in marketing at Carrier was castigating all the salespeople for not making sure that the customer knew that they had to pipe counterflow. And it said, in this 1979 memo, it said that the amount that you lose if you don't pipe counterflow, if you pipe parallel flow, in other words, if this is my cooling coil, this is the air, and instead of counterflow, if I screw up and I pipe it parallel flow, you lose between 15 and 20% capacity. In a little 4-row coil, you probably lose 20. By the time you get to an 8-row coil, you're probably losing 15. 6-row, which is probably the most common thing we would see in air conditioning today, a 6-row would be losing, 17 or 18% capacity because it was pipe drawn. Only because it was pipe drawn. Everything else was done correctly. So that's how much counterflow makes a difference. Chiller heat exchangers, any heat exchanger you want to think of. Plate and frame heat exchangers, same way. If you're using any kind of a plate heat exchanger, they have to be counterflow. When you don't have performance and nothing else makes sense, the very first thing to look at is, did we pipe it counterflow? And heating is the same way. It's just that heating is typically a 1 or 2-row coil, so you don't lose quite as much. 2 rows, you're probably not going to lose a whole hell of a lot. Okay. What we're going to end up talking about next time is economizer cycles and how we control the dampers and the building pressurization to make sure that all works. And after that one, we'll start into mechanical refrigeration and chillers and condensing units and that kind of stuff.